and gentlemen, recording has started. So, up on the board, and if you're listening at home, you're going to hear a big rustle. It's me adjusting the microphone. All right, up on the board, we are looking at a set of data and the graphs that I made out of that data for time and position data related to the car, related to the ball. And I went through last Friday on how to make these graphs, how to make them look the way they're supposed to look, and et cetera, et cetera, et cetera. We good with those? Okay. Here's what I want to do next. I am going to take this car data and plop it here so I can do some calculations with it. And the first thing I want to do is I want to calculate the average velocity for this car's trip. So in order to calculate the average velocity for this car's trip, what do I have to know? The change in displacement. So let's go displacement, right? And then the amount of time, right? And so we said that this is our formula for average velocity, right? Delta x over t. And that we can break that down to make it look a little bit more like this, okay? So for this trip, right, what was the car's initial position? Zero, right? That car started at 0, right? It says 0 is the initial position. So I'm going to plug that in there for x initial, right? What was this car's final position? Where did it end up? Based on my data here. 9.887 meters away. So I'm going to plug that in here, 9.887 meters. Okay? And then I'm going to do that over the time that it took to do that displacement. So I take a look. The initial time I started off with was 0, right? And then what was the amount of time that it took for us to complete that displacement? 21.19, so that's going to go here. Okay, 21.19 seconds. So because I asked you all to pull out your calculator at the beginning of the class, you've got these numbers, and it turns out to be 0.4665, and I think that's proper rounding. Oh, wait, what's after the 5?
8.
Okay, because how many sig digs here? 4 sig digs here. 4 sig digs here, so our answer should have 4, right? But if it's 4.6658, that means that we should round that to 4.666 meters per second. Okay? And that would be the average velocity for that car's trip, which is great. But what is that telling us? Or what is that not telling us? If this is the average velocity, go ahead.
It's not telling you the speed.
It is telling you the speed, because we said velocity includes speed. Right, Jill? We could call this, that's true, technically it doesn't tell you that, okay? But if we say that the direction that that car was moving in was the positive direction, right? If we call that the positive direction, which we are perfectly entitled to do, we could say that because those positions are all positive, the velocity was positive as well, okay? This is the average velocity. What does the average of something tell you? It's a hard question, right? What does the average of something tell you?
It just tells you what its velocity was, like the median velocity.
Good, like the median velocity. What does your grade point average tell you?
Median grade.
Your median grade, or what kind of overall student you are. But what does your grade point average not tell you? Does it tell you what you got in math? Does it tell you what you got in physical science? Does it tell you what you got in English? No. An average is a big picture. So the average velocity for this car was 0.4666 meters per second. But do we know what that car was doing at any particular point in time of its trip? Not really. And that's what the section of your lab is kind of all about. So, here's what I'm going to do next. That set of data right there. Can I calculate the velocity? This is the starting line. This is the first tape mark. Can I calculate what the velocity was through that interval? Sure. I can figure out what the displacement was during that time. I can figure out what the time was. And it's actually pretty easy for this first interval because where does this object start? 0. So its displacement is just going to be 1.043 meters. The time it takes to go that distance was 2.31 seconds. And once again, because you all have your calculator out, you can figure out what the velocity was, or the average velocity was, between the starting line and the first tape mark. Okay. Actually, we should probably cut this off, right? Because the top number is 4 significant digits, the bottom number is 3 significant digits. So we should probably cut that off here to 0.452 meters per second. Okay? So what are we seeing about the velocity of this object from the start to the first tape mark in relation to its velocity for its entire trip? 0.452, 0.466. Pretty close, right? Next thing, I'm going to jump ahead a couple marks. I'm not going to do all these for you. But let's take a look at this interval right here. This is tape mark number 4, and this is tape mark number 5. Can I calculate what the average velocity is for that section right there? Sure. Okay? I need to know the displacement during that interval. In order to know the displacement during an interval, what do I need to know?
Final and initial.
Final initial. So, Kraft, what was this car's final position during this interval? 9.887 meters was its final position. Minus, for this section right here, the initial position being 6.543 meters. Right? Does that make sense? And then I also need a what?
Time.
I need a time. But I don't want the whole time, I just want the time over which this displacement occurred. So how am I going to figure that out? Rachel?
21.18 minus 14.58, which is 16.
Okay? And so, now you can run that through your calculator, and you can get an average velocity that occurred from tape mark 4 to tape mark 5. Good. What is it?
0.505900.
Okay?
That's not the same day. Is it?
It's not sick. It would be 5 points.
Never trust you again.
That's me.
I mean, you gave me the wrong sig digs.
But that means I was right.
It's not the first time you've been right in this class. I mean, let's
I'm not right now.
you're right enough. All right, so this is the average velocity from tape mark 0 to tape mark 1. This is the average velocity from tape mark 4 to tape mark 5. This is the average velocity from tape mark 0 to tape mark 5. What are we seeing about all those average velocities? Pretty close, right? Because what did you see about that car as it was rolling along the floor? Stayed about the same speed. In your lab report, in the calculations section, I need you to calculate the average velocity for the first section. And then I need you to calculate the average velocity for the second section, from tape mark 1 to tape mark 2. And then you got to calculate the average velocity for tape mark 2 to tape mark 3. And then you got to calculate the average velocity from tape mark 3 to tape mark 4. See, I did that. I didn't do that yesterday. I put them in different order. I'm going to show you another one here. I put them in different orders, and people got mad. So you know. Emma, go ahead. Hey. Questions? Emma, go ahead.
Do it from 0 to 5 also.
You're going to have to look at the total average velocity. Yes. So that would be like that would be like a purple line, right? Okay. All right. Say it. Well, people they noticed. So, and actually. Well, it was actually because I'm going to show you another set of data, and I didn't do them in the same order on both sets of data, so people got it. So I just decided I might as well just do a rainbow because I can remember what order I did it in then. Yeah, so, okay. All right, here's what I would like you to do next. Here's what I would like you to do next. Okay. Here is position and time data for the ball as it rolled down the hill. So, if you have your set of data, you can use your numbers. If you don't have your numbers, here's numbers for you. I want you to calculate 3 things for me. First thing I want you to calculate, the average velocity for the entire trip, the ball's entire trip. Then, I want you to calculate the average velocity of the ball from the starting line to the first tape mark. And then I want you to calculate the average velocity of the ball from the 4th tape mark to the 5th tape mark. Like I said, if you have your data, do it with your numbers. If you don't have your data, use mine. 2 minutes, go. Yeah, use your average times. Yep, those are your times, your average times. Okay?
The difference between each one of
No,
them.
you'll still see the same relationships. Everything that I'm talking about here applies to. I mean,
Remember leaving previously?
it's not a mistake. It's just a different way of measuring distance. That's all. Right? All the relationships will be exactly the same. Do the averages. Remember, the reason why you took free trials was to get an average, Haley. So the only times I care about are your average times, because that's why you did all those trials. So yeah, so you basically, Haley, you have 2 sets of data. You have a position column and you have an average time column. And those are the only data that I really want. Okay? As well as you can, yes.
What if we only have like our positions are like 1, 0, 1, 2?
Technically, they're more than that because the ruler that you used has more precision than 1 meter. Technically, it's that ruler, the tape measure that we were using, should go to 3 decimal places. So you're still the same thing. It's the same gradation. So your measurements are actually 1.000 and 1.500. Does that make sense? Yeah. Ben, is that your question or okay? seconds. 30 more seconds.
Repeating sign, right? You just round it to the number of sig digs, right? So if you need 3 sig digs in this number,
That's
right? If it's 1.81881, it's just 1.82.
Because the ramp that we had was 5 meters long.
And for multiplication, we do it with a number that is single.
That's multiplication individual. And that's what you're doing in this one.
You need zeros or sig digs.
Zeros are significant. Yeah.
All right, so let's discuss. All right, so let's discuss here. So the ball is much more interesting. The ball rolling down the hill is much more interesting to look at than the car, because physically, what did you observe about the ball as it was rolling down the hill? It goes faster and faster and faster, right? This purple value represents the average velocity of that ball for its entire trip. Does that really do us any good when we're talking about a ball rolling down a hill going faster, 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 faster? The only thing it tells us is that half of the time the ball was going faster than that number, and half the time the ball was going slower than that number. And when we go to calculate the velocity at the beginning, we see it's lower than the average velocity. And then when we see the velocity of the ball at the end, it's greater than that average velocity, which it should be. Okay? Now, all right, hey, listen. This next part, I know you guys are doing calculations for your lab report. If you don't listen to this next part, you're going to miss another part of your lab reports. Okay? So, for the ball, once again, I need you to calculate the average velocity during the first interval, and then I need you to calculate the average velocity during the second interval, and then I need you to calculate the average velocity during the third interval, during the fourth interval, during the fifth interval, etc., etc. Okay? Yes, Ben?
So it's like, again, the 0 to 1 and 2.
Yep. Okay. Just like that's why I got the color codes going on here. Yes, Ben? This is your lab report. Haley, this is the calculations section of your lab reports. Okay? Okay. We haven't had any calculation sections in lab reports up until this point, but you do for this one. Okay? All right.
What do we write in the calculation section?
Read your description of what you're supposed to put in. It's actually a data table. It's a calculations table, I guess. All right. Next part. Once again, this part deals more with your conclusion statements. Okay? I need you guys to do me a favor. I realize the difficulty of the tasks that I'm about to ask of you, but try your best. I need you to remember back to when you took pre-algebra. Ouch. Ouch. Pre-algebra. All right. The reason why I need you guys to remember back to when you took pre-algebra Okay. So, bulls. Another way, this is conclusion statement, everybody. Another way that we can talk about the slope of a line is by knowing what? Slope-intercept form, which looks like y equals mx plus b. Okay? Where what is the slope of that line? N. Okay? All right. So now, here's a jump that I need you guys to make for me. These y's and x's relate to any line in general. This isn't any line in general. This line in particular is relating what two measurements that we took? Position and the time. Where is position on this graph?
Y-axis.
Y-axis. So when we're doing y2 minus y1 to calculate the slope of this line, what unit would our answer be in? Meters. And when we're doing x2 minus x1, what's on the x-axis of this graph? Time. So that's going to be measured in what? Does that unit look familiar?
Hilarious.
Yeah.
That's very funny.
So,
X is time.
because that's what's on the x-axis, right? So if we calculate the slope of this line in particular, what is that slope telling you about this motion? The slope is telling you its velocity. Right? Bulls. Going back to our slope-intercept form, right? Y equals mx plus b. Here's our equation for our line, right? But remember, we changed y into what? D for distance, right? And then we changed x, no, I shouldn't use that. We changed x into t. Meaning, for this line in particular, the slope of this line is equal to 0.4628. Good with that? So the slope of this line is 0.4628. Hold on a second. If we go back 2 pages to here, what did we calculate was the average velocity for that car as it's on its trip? 0.4666. And here the slope of this line, too far, is 0.4628. Notice anything similar? Pretty much the same, right? So the slope of this graph is telling us the velocity. Why does the car graph have to look like this?
Because it wasn't accelerating more, because it was sort of
What did we say about the velocity of the car? It was what? Constant. Meaning, what has to be constant on this graph? The slope has to be constant. What does a graph with a constant slope look like? A straight line. Are you ready?
the other one.
Here's the ball. Is the ball a straight line? No. Why?
Constant.
It didn't stay constant. If we take this ruler and we use the ruler to sort of look at the slope of this line, at the beginning of this graph, is this a steep slope or a shallow slope? Shallow slope. But as we go along, farther, 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 what's happening to my ruler? Steeper, 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 steeper. Because what was happening to the velocity of this ball? Increasing. The name of your lab is position versus time graphs. It's looking at the analysis of this graph versus this graph and why the different motions produce the different graphs. Got it?
Got it.
Okay. You ready to apply some knowledge?
Yep.
Yeah. All right. What? Go to you. All right. Here's your lab that you picked up on the table when you or on the tray when you walked in today. Okay? tray. We're almost done with sitting in chairs, promise. On this lab that you picked up on the tray when you walked into the room this morning, on the middle of the front page, there is a section that says preliminary questions. The preliminary questions are predictions. Okay? You will not get them counted right or wrong. But what I would like you to do is the following. There are 3 graphs here. They're position time graphs. And underneath those graphs, it asks you to make a prediction about what a graph representing this motion described below it would look like. So there's only going to be 1 line on the first graph. There's going to be 2 lines on the second graph, one for an object moving with a constant velocity, one for an object moving backwards with constant velocity. There's going to be 2 lines on the third graph. If you would like, I have a box of colored pencils here. So if you would like to make them in different colors, feel free to do so. I would like you, listen, I would like you to take the next 2 minutes and in your lab group, make some predictions about what those graphs would look like. Go.
Okay, so
The one's a straight line.
are you guys ready with science?
All right, everybody. So, as you can see, if you're watching the class recording, I put the spotlight up because I want to highlight these things individually. So, the first one, we said that, we just discussed that what tells us about the velocity on a position time graph?
The slope.
The slope. Okay? So, the first one I had to draw was for an object at rest. What's the velocity of an object at rest? This isn't a hard question.
It's
0, right? Okay? So what does the slope of this line have to be?
0.
Horizontal line has a 0 slope, right?
Yeah.
Okay? So, an object at rest would look like a horizontal line. Now, does your horizontal line have to be in the same spot that mine is? No. Where it is on the y-axis tells you, or how high up it is on the y-axis tells you where that object is, right? If I drew it down here, right, is that still an object at rest? Yeah, it's just an object at rest where? At 0, at the starting point, right? So, any horizontal line is fine. Okay, good there. Next graph. Next graph would look like this. Okay? Object moving forward, object moving backward. What's the only thing that's different about them? From a velocity standpoint, they have a different what?
Slope.
Well, yeah, but from a general velocity standpoint, we said velocity tells you magnitude and direction. An object moving forward and object moving backward have a different direction, right? Can you have a negative slope? Yeah, it just means the line's tilting downward. These are both constant slope lines. It's just that the red one has a positive constant slope, the blue one has a negative constant slope. Okay? Good there? All right. Last picture. All right. So, the red one should look, now wait. Before you erase things, these are predictions, all right? They're not right, well, they can be right or wrong. I'm not going to mark them right or wrong, okay? The red one is the graph we just talked about. That's the ball rolling down the hill, right? The blue one, though, in order for something to slow down, the slope has to become less steep, right? If you look at this blue graph at the beginning, how steep is its slope? Pretty steep, right? But as it goes along, farther, what's happening to the steepness of that slope? It's decreasing. That object is slowing down, okay? That is not the only right answer. Did anybody draw this?
Yes.
Okay. correct answer? Yeah. What's different about this blue line versus this purple line? They are flips. It's what, Kraft? It's going backwards. This purple line starts off with a real steep slope, but which direction is it sloping in? The negative direction, meaning it's going backwards. But as it goes along, right, it's flattening out. The slope is becoming less steep. Blue is slowing down, purple is slowing down as well. Okay? Got it? All right. Going back to the lab, there are some things I want you to cross out. On the first page, where it says equipment setup, cross out number 1. You're not going to do that. Okay? Cross out number 3. You're not going to do that either. You are going to do number 2. That says, hey, plug the motion detector into the lab quest. Okay? Let me do this. All right. On page 2, you can cross out the entire section that says preliminary graphs, the entire section that says graph 1, constant positive velocity, and the entire section that says graph sketches, preliminary graphs. You're not going to do any of that. You are going to pick it up at position versus time matching. Okay? You're going to do position versus time matching. You're going to answer the questions that are at the top of page 3. And then down at the bottom of page 3 where it says velocity versus time matching, bottom of page 3, cross that out too. You're not going to do velocity versus time matching. And then none of the back page, because that all relates to velocity versus time matching. So you're only doing the part of position versus time matching. Okay? Part of page 2, yes. And part of page 3. All right. To get us ready for lab, you need 2 things. You need LabQuest, which are in the cabinet marked LabQuest, back by the clock. You need a motion detector, which is in the cabinet marked motion detector by the big bike wheel over there on the side. You may go out in the hallway, find a flat wall to work against, because that's what you're doing. Be quiet, because other classes are in session, please. Nope.
Ben, get the lab quest. Okay.